Hey everyone, in today's video we're going to be going over differentiating inverse functions. This subject can be found in an intro college class such as Calc 1, but in the AP Calculus A, B, and BC curriculum, we're going to be on topic 3.3 as seen here. Let's start with a little review on how an inverse function works. If you're pretty solid on your Algebra 2 and Pre-Calc, then you can use the chapters below to skip to the real calculus work. So, this right here is going to be the notation for an inverse function. And what this statement means right here is that we are going to switch the two variables and then we're going to solve again. So let's take an example if you don't know what I'm talking about. So here we're going to take this y and this x and we're going to switch them. So we're going to have x is equal to y squared. Now we're going to solve for this new y variable right here, and we're going to get the square root of x is equal to y. So let's have another example just to illustrate this again. Let's say we have an equation like 5x squared plus 3x plus 4 is equal to y. Well, we're going to take this, we're going to swap the variables, and we're going to get 5y squared plus 3y plus 4 is equal to x. Then we would solve for y, and you would do the same process here. You just solve for y, and then that would be your inverse equation. It's the same process no matter what two variables you use. So now we're going to relate this to tables and graphs. Let's take a look at the equation we just found the inverse of. Y is equal to x squared. We are now going to reflect that equation over the line y equals x. So this right here is going to be y equals x. So let's see what we get. You should know what this equation right here is. This is a pretty common equation. This is going to be the graph of root x. And so what we have for this is that we can conclude for all cases the graphical inverse of a function can be found by reflecting over the line y equals x. So again, this is y equals x. We reflected y equals x squared over the line, and we got root x. And we found that root x is the inverse of y equals x squared. So again, our conclusion is the graphical inverse can be found by reflecting over y equals x. So now let's take a look at this table over here. For any given point a, b, let's take a look at 3, 9. All right, so we have a, b, and we're going to be looking at specifically 3, 9. All right, now this point 3, 9 is in the domain of f of x. But let's look down here. The point 9, 3 is in the domain of square root of x, so is in the domain of the inverse function. This is true as well for points such as 2, 4 and 4, 2. So now we know that for any point a, b in f of x, then the point b, a will be in the domain of f, it looks like to the power of -1 of x, so the inverse function. So now let's get to some real calculus work. What do you notice about the slopes of the two equations? Now remember, the slope is also known as the tangent line at a point, which would be your derivative. So once we set the inverse function to g of x, what do you notice at these slopes? Pause the video and see if you can find a pattern. Well, we can see at any given point AB, so we're going to bring out this concept again of a point at AB. At any point AB, the slopes of the two equations will be reciprocals where x is equal to a for f of x and x is equal to b for the inverse function. So let's say for the slope at 2, 4, the tangent line at 2 will be 4x minus 4 for f of x. All right, and how I found that is I found the derivative, which is 2x, right, which is 2x, become 2x. Then I plugged in the x value, so I got 2 times 2 equals 4. Then I use point slope formula, which is y minus y1 is equal to m times x minus x1. All right, and I would get y equals 4 times x minus 2 plus 4, which is equal to 4x minus 4. And so if I were to draw that line here, I would get something that looks a little bit like, that's a little bit hard to see, a little bit like this, right? I'm going to tell you right now, if we did the same exact thing, we would get the tangent line at 4 for the inverse function, right, for the other point here. So we're not using the same point, we're going to use the inverse point because we have to switch it to be a. But we're going to get something that looks a little bit like this. I'm going to tell you right now that that function is actually going to be 0.25x, which is equal to 1/4 x plus 1. Okay, and we can see here that 4x and 1/4 x is going to show reciprocal slopes. So let's take that inclusion. We're going to make the following points. Since they are reciprocals, this following is true. The top equation we kind of already solved for here when we set g of x is equal to the inverse function, but the bottom one may take a little bit more thinking. So let's say we have, and let me just erase so we have a little bit more room here. Let's say we have the point AB again, where f of a is of course equal to b. Now let's say we plug b into the inverse function to get g of b. Well, g of b should give us a. All right, if you need a minute to think about that, pause the video and reflect on what we've gone over so far. Hopefully that will help, but if you do need more assistance, make sure to comment below and we'll always answer your questions. Either way, now we know that g of b is equal to a. It therefore follows that g prime of b is equal to f prime of g of b, and now we'll just replace b with x, since x is of course the more commonly used variable, and that is how we get to this key equation. All right, now let's prove this formula by quickly deriving it, and then we're going to do a practice problem. So again, we're going to set the inverse function equal to g of x. Now our proof before showed that when we plug in f to get the inverse function, then we plug that value into the original function, we'll just get x of again. So let's say that f of g of x is just going to be equal to x. And now we're going to differentiate both sides, and then we're going to get, by chain rule, f prime of g of x times g prime of x is equal to 1. It's a simple chain rule, and then obviously x derivative of x will be 1. And now we're going to divide both sides by this here, and we're going to get g prime of x is equal to 1 over f prime of g of x. Now we know again up here we can just go back and resubstitute this into our equation. Therefore, we're going to get f inverse function, the derivative, got to make sure we have that prime symbol, is equal to 1 over f prime times the inverse function when we plug into x there. And that's it. We've proved it two ways that this is going to be our equation to find the derivative of the inverse function. Now, you don't need to memorize this formula for your exam if you think you can derive it on demand, but it may be a good idea to have it in your calculator for the calculator session, especially on the multiple choice when time will be tight. Now let's get into some practice. On your test and on the AP, you'll probably see many inverse derivative questions where you must find the values using tables. So here's an example. Pause the video and see if you can solve it yourself. Okay, so let f and g be inverse functions. Use the table below to find g prime of -2. So we're assuming that g prime is going to be your inverse here, of course, right? And often the question will have some statement that's similar to that. So the following table is going to list a couple values of f prime, g, and f. So based on the formula we derived earlier, g prime of -2 is going to be equal to 1 over f prime of g of -2. So we need to find g of -2. And we see right here that's just simply equal to 5. So we're going to set this equal to 1 over f prime of 5. We know f prime of 5 is going to be, we're going to go right here in the table, we're going to see that it's -0.5. And so what we're going to get that is we're going to get 1 over -0.5 is equal to this guy right here. And of course that leaves us with a final value of -2. So g prime of -2 is simply -2. All we did was follow our formula, and the most important thing to remember is that an inverse function's output for a specific input is going to be the same as the input for that specific output of the normal function. That's a lot, but if you just review this video again, I'm sure you'll understand what we're talking about. So, that's all for this video, and if you liked the video, drop a like and subscribe. Thanks.